All right, hello IB and welcome to Calculus. We've started a little bit of C and D discussion the other day about what calculus really is, how the idea of a limit is used in calculus, and now we're backtracking and going back to 14a, which is really how do we work with limits and what are they really? Let's figure out a little bit more about them. So we've already kind of discussed that the idea of a limit is used in calculus as you're approaching a point. What does the gradient wind up approaching? So consider the function x squared. We've used this a few times now. And let's just think for a moment what happens as our x value approaches 2. So if we just think about the function x squared, we have a parabola. It's our parent parabola, quadratic function. So there it is. F of x equals x squared. And we have an x value at 2. So let's say here is 2. All right, so x is 2, that means y is going to be 4. So we already know a couple things about the function, so therefore when we start to analyze it, the question really is, what is our limit as x approaches 2 from the left and from the right? So if I wind up choosing a point closer to 0, and then I travel closer and closer and closer and closer to this point 2, what does my y value wind up approaching? So just looking at the table here, as we start at maybe 0 or 1, as the table suggests, we start at 1, and we travel closer and closer and closer until we get really close to 2. Our y value starts at 1 and gets really close to 4. And that's coming from the negative direction, from the left. So let's see what happens as I travel from the right. So coming from, let's say, an x value of 3, and then we get closer and closer and closer to 2. What's my y value doing? My y value is starting up at 9, and I get closer and closer and closer to 4. So what we can say is we're getting so close to 4. We actually have a point at 4, at x value of 2 and y value of 4. So we can say that we actually are approaching 4. From the left and from the right, we wind up getting the same y value. So as x approaches 2 from the left, f of x approaches 4 from below. And as x approaches 2 from the right, then f of x approaches 4, but from above. Okay? So the way that we've been writing this up, or just learning to write it up, is the limit of x squared, which is our function, as x approaches 2. And if you just see the number 2 there, that means we're thinking it's approaching from the positive direction and the negative direction. Either direction you approach 2 from as an x value, you're going to approach 4 as your y value. So this whole idea of what we're approaching as the y value, as your x approaches a certain value, is the idea of a limit. And sometimes you're actually going to have a point at that value. So we can say you actually are going to get the intended value of the function at that point. But sometimes you have a limit as x approaches a, but it doesn't actually reach a. So you might not actually have a point at the intended value. However, you are getting so close that we round it off and we say we actually have a limit because we approach a certain number. We get so close that we can kind of almost like you round it off, okay? So we say that if your function actually does get so close to a certain value, it converges to that value. So it converges to a as x approaches little a, all right? So thinking of the little a as your x value and the big A as your corresponding y value, possibly, if you actually have a value there, or you're just getting really close to some y value. Doesn't matter if the function exists, if the function has a limit that has a function that exists at a or not. Doesn't matter if you actually have a value at that x value of a or not. All right, and we're going to look at an example here in a moment that will show you what I mean by that. So here's an example of what I meant. So is a limit just the function value at that point? So is it just the corresponding y value? Will that always happen? Okay, so for example, if x is approaching some value c, could I just substitute c in and get the y value corresponding when x is c? Let's see if that actually happens. So to do that, we're going to take a look at y equals 4x plus x squared divided by x. If I substitute in x equals 0, just think for a moment what is going to happen, all right? So I've got y is equal to, I'm going to substitute 0 in. Issue is we are dividing by 0. And a few units ago, we looked at the fact that if you have a 0 in the denominator, or when your denominator is set equal to 0, you wind up getting a vertical asymptote, okay? So we might possibly have a vertical asymptote here or an undefined value here. So we've got some kind of issue occurring that we need to analyze a little bit further, all right? So I can't just substitute in 0 in this problem because I'd be dividing by 0, and we might have some kind of undefined value. So let's continue and see what else we can kind of figure out. Take a moment to pause the video and graph this function in your calculator and go ahead and draw a sketch of what this graph actually looks like. If you sketch this function, it looks like a linear function, and it looks like the function y equals x plus 4. So I have a gradient of 1 and I have a y-intercept of 4. However, if you trace the function and you look at it a little bit closer, what you actually realize is that we don't have, or if you look at the table of values, you notice that you have an undefined value right at 0, which is what you guys were being asked to analyze. If you substitute x in as 0, what's the y value? So if you look at the table or if you look at your graph and trace, you're going to notice that you have a hole at x equals 0. So when we discuss it as a limit, if I approach this x value of 0 from the right, so this little plus sign saying come toward 0 from the right, I'm still going to have a y value that gets really, 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 really close to 4. And if I approach it from the left, which is what this negative value means, I'm also getting a y value that's very, very close to 4. However, at 4, I actually do not have a corresponding y value because I have a hole in my graph. Because I have an undefined value when x equals 0. So therefore, I can still say that my limit of this function as x approaches 0 is going to be 4 from the right and from the left, just because I get so close to that value that I can go ahead and say that's what it's going to approach from both directions. All right? So this is an example where you don't actually have a corresponding y value for this function, but because we get really close to it from both directions, we can go ahead and say we're going to approach 4. So algebraically, how would I actually wind up working out the limit without looking at the graph and analyzing the graph? So we are going to use factorization to wind up looking at limits, to wind up simplifying this limit or finding the limit. 4x plus x squared, I can go ahead and take out, so my limit as x approaches 0, proper notation to rewrite that limit as x approaches 0 until you actually take the limit. I'm going to factorize out the x, so I'll be left with x plus x in brackets divided by x. What you guys will notice is here I have a common factor, and I'm going to simplify that common factor, but when you guys see that common factor, you wind up getting a point of discontinuity at at x equals 0. So when that common factor is equal to 0. So that is where we were getting that hole in our graph at x equals 0. So I will reduce, so I'm left with the limit as x approaches 0 of 4 plus x. So even though I've gotten rid of that factor of x, I have noticed and I've analyzed that I do have a point of discontinuity at x equals 0. Now that I have simplified my function and I have the limit as x equals 0, 4 plus x, I can go ahead and substitute in 0, and I won't get an undefined value anymore. So if I substitute in 0 for x, I am left with 4. Once you actually substitute in the x approaching that 0 value, I cannot write that limit piece because you've taken the limit. So the limit of x approaching 0 from the right and left is going to reduce down to 4. So what we say is our function converges to 4. So let's take one more example just to go through what we just bring together everything we just talked about. We're going to start by trying to find the limit as x approaches 2 of the function x minus 2 and x squared divided by x squared minus 4. Again, if I substitute 2 in at this stage, all right, I'm going to wind up getting 2 minus 2 divided by 2 squared minus 4. Again, I'm going to get 0 over 0, just undefined. I cannot do that as it is. So let's do a little bit of factorization and see if we can analyze the graph or this function a bit more. So I have the limit as x approaches 2, and we're going to go ahead and factorize the denominator into x minus 2 times x plus 2, which means I have a common factor of x minus 2 and x minus 2. So what we've just found is that we are going to have a hole in our graph. We're going to have a point of discontinuity when x minus 2 is equal to 0. So therefore, at x equals 2, we have a point of discontinuity. So already we know that we are going to have point of discontinuity or a hole in our graph. So let's continue. We now are looking at the limit as x approaches 2 of 1 over x plus 2. Now remember, this function here, same one, we just simplified it down, so you can graph it at the beginning or graph it here. But the case is, you guys are going to have a vertical asymptote. Remember when our denominator is equal to 0, so when x plus 2 equals 0, you guys wind up with a vertical asymptote. So think back a couple units. So we have a vertical asymptote at x equals negative 2. So we now know 2 pieces of information about our graph that you might not have seen just by graphing it in the calculator or just by looking at the function itself. So already now we've got 2 very, very fine details that we can include in our graph and in our analysis. However, we are now at the point that I can safely substitute in 2. So now I can say that my limit as x approaches 2 of 1 over x plus 2 is going to be 1 over 2 plus 2, which is going to be 1/4. So as x approaches 2, we are going to approach a y value of 1/4. So now we know 3 key pieces of information about our graph that we wouldn't have known before, and now we can actually graph it extremely accurately. All right, guys, we'll do more of this in class. Have a great night.